Tsinghua University in Beijing, China. This was my alumni. He received a PhD in electrical engineering from Princeton University. So his advisor is Professor Vincent Ford, a famous researcher in the field. Husheng worked in Qualcomm for 2 years. San Diego. Then since 2007, he joined the ECS department at the University of Tennessee, Knoxville, as an assistant professor. So his research is mainly focused on wireless communication. Dr. Li received several awards, including the Best Paper Award of the U.S. Journal of Wireless Communication Network, and also Best Paper Award from IEEE ICC Conference in 2011 and IEEE Smart Gridcom 2012. And he also received the Best Demo Award from IEEE GoCom 2010. So let's give a warm welcome to our doctor.
So good afternoon, everyone. Thanks for coming to my talk. The title of my talk is Analysis and Design of Information Networks for Cyber-Physical Systems with Applications in Smart Grids. So this is the outline of my talk. First, I will explain the main research topics in my lab, and then we will discuss 3 topics. All of them are related to cyber-physical systems. And finally, I will give the conclusions. So let's begin the first thing that I want to explain. These are some pictures in my lab. And my lab is called TigerCom. It's because one of the characters, the Chinese characters in my name means tiger. And since I joined Qualcomm, and I hope my lab is called TigerCom. It's similar to Qualcomm or Broadcom, right? So basically, our research is supported by NSF projects and some projects from DoD and Oak Ridge National Lab. We have got some Best Paper Awards and some Best Demo Awards. And this slide shows our current research topics on cyber-physical systems and smart grid. Basically, we are designing communication network for power systems. So our research is supported by Oak Ridge National Lab. We are designing the communication network for power flow control and also the distributed energy generation inverters. And we got a NSF CPS project to study the communication network for protections in power grid. And we are also collaborating with the Oak Ridge National Lab and another company called ITT to study the GPS spoofing stuff. So these are some selected publications on the topic of smart grid. And we also did some research on cognitive radio. We are supported by NSF to study, say, the spectrum sensing using quick detection, and also the wideband cognitive radio processing. And we also wanted to use a random field to model the spectrum activities in cognitive radio. And we are also supported by NSF to study the social behavior in cognitive radio, and also supported by Army Research Lab to study the heterogeneous cognitive radio network in the battlefield. And we are also supported by Air Force summer faculty program to study the jamming, how to do the cognitive electronic warfare. And actually here I also want to mention some of our minor study. We used a machine learning to do the social network analysis. We studied the adolescent health issues. For example, we studied the impact of social norms and networks on the drinking behavior among youth. And we published one paper in Sociology Association annual meeting. So I can also claim that I'm a sociologist. So now, since this talk is on the cyber-physical system, so Before we get into the details, we need to explain the concepts and the challenges for the information or communication network for cyber-physical systems. So now many people are talking about cyber-physical systems. And if you ask 100 people, you will get 100 definitions of cyber-physical systems. So there's no rigorous definition for cyber-physical systems. But no matter how you define it, we have several essential components in a cyber-physical system. Since we are talking about a cyber-physical system, you must have a physical dynamics, right? So the physical dynamics could be, say, a power grid, right? The voltage oscillation in power grid, right? Or the tracks of UAVs, or the motion of robots, right? And we want to control this physical dynamics. So we need sensors, right? And these sensors need to send their observations to the controller or some computing devices. Then we have a communication network. Since I'm a communication guy, my research is focused on this part, how to design the communication network. So basically, we have a physical dynamics, we have controller, we have sensors, and we have a communication network. This is an illustration of the information flow in smart grid. For example, at your home, you may have a wireless receiver to receive the current power price, such that you can control your power consumption at your home, right? Or you can use a wireless router to control the power consumptions of your appliances, right? When the price goes high, I can turn down my air conditioner, right? Such that I can save some money. Or if you want to control the distributed energy generations, then you need feedback control for your power electronics interface. And if you want to do protection, you also need communications. For example, if we want to do differential protection for a transmission line, right? You put two sensors at the two ends of this transmission line. So this sensor measures the current flowing into this transmission line. And this sensor measures the current flowing out of this transmission line, right? Then these two sensors need to communicate with each other to check whether the two measurements are equal to each other. If the two currents are equal to each other, then everything is fine. But if they find that, okay, this current is not equal to this current, then something must be wrong, right? Because we have Kirchhoff's law, right? There must be a fault at this transmission line, right? So these two sensors need to communicate very fast and very reliably, right? So we also need communications. And the communication can improve the efficiency, reliability, and robustness of the power grids. So since we have so many applications of communications for cyber-physical systems or smart grids, then we have several major challenges. The first problem is quite fundamental. That is, if we want to control the cyber-physical system, or you can also consider it as a networked control system, then how much communication is needed for the purpose of the control, right? This is a very fundamental question. Then if we have some communication resource, how can we efficiently design the communication network for the purpose of control of the physical dynamics? And the third problem is how to keep the security of this cyber-physical system, right? Because we know if someone attacks your physical dynamics and your physical dynamics collapse, then there will be a big damage, right? If you have a blackout, then you lose millions of dollars, right? So the information security is also important. So basically, our research focused on these three problems, and in this talk, we will discuss these three problems separately. And our philosophy of research is, since we are studying the physical dynamics, and we are designing the communication network for the physical dynamics. So for our analysis and design, we need to incorporate the characteristics of the physical dynamics. So when we study the communication design for smart grid, we need to know how power grids operate, right? Of course, that also adds a lot of burden to me. I have to ask my students to take courses on power systems. So it takes some time to understand how power system works. Then let's begin from the first question. What's the minimum communication requirement for controlling a system. Basically, we want to study this problem from the viewpoint of thermodynamics. And then we use information theory to analyze a more finer structure. We know for networked control system or separate physical system, there have been many studies on the communication requirement. So when the sensor sends information to the controller, and the controller wants to stabilize the system, we want to know how much communication, how many bits should be transmitted in each second, right? Actually, there have been a lot of studies on this topic in the community of control systems. For example, these guys there, they found that if you consider a deterministic dynamics with unknown initial state, then the communication capacity is determined by the topological entropy of the dynamics. And Sahai in 2006 found that the communication network need to satisfy the anytime capacity if you want to stabilize a random dynamical system. And you also need to study the sequential rate distortion to stabilize the control of random dynamics. But in our research, we want to take another approach. We want to use entropy as a metric to measure the fitness of the physical system. We know if a system is in a high entropy, it looks something like this. And actually, when I was in my college, my dormitory looks like this. But after I got married, my room looks like this. So it's in a low entropy. We know we don't want a high entropy, right? If the system is in high entropy, it's quite uncertain, right? It's messy, right? So we hope that the physical dynamics could be in low entropy because we are more certain about the system, right? The system state is more focused on a certain location, right? So actually, in 1944, the very famous physicist Schrödinger wrote in his book What is Life? He proposed to use entropy to measure the fitness of a individual person, right? And we can also borrow this idea for the physical dynamics. So we can use the entropy to measure the fitness of the physical system, right? And we hope that we want to decrease the entropy of the physical dynamics. Then here we propose a model. We assume that the physical dynamics works in this way. It works in many cycles. In each cycle, we have 3 stages. In the first stage, we have a certain system state. And then we have some random factors. For example, oscillations in the load in power grid, right? Or the oscillations of the generators in the power grid. So those random factors will increase the entropy of the system state, right? So we get a new system state X0, which has a higher entropy. Then the sensors makes observations on this guy, and it sends some messages M to the controller. The controller take action A, and hopefully this action will decrease the entropy. So we get a new system state, and hopefully this system state has a lower entropy than this X0. And then we do it again, right? So the whole system works in cycles, right? Then let's suppose that the entropies of X0, that's X0 here, and X, that's the X here, right? We assume that the entropies are H0 and H. And hopefully, the entropy here, H, is smaller than the entropy here, H0, right? Then our question is, what's the communication capacity requirement if we want to reduce the entropy from H0 to H, right? So this is the problem formulation. And this problem, actually this problem reminds me of some model that I have learned in thermodynamics. We know in thermodynamics there is a very famous model which is called Maxwell's diamond right, which was proposed by James Maxwell in 1871. So he proposed this model. He demonstrates that the entropy of a system can be decreased. So let's take a look at this example. We have a container. In this container, we have many gas molecules, right? And we have a door in the middle of this container. And we have a daemon which can control this door. Actually, he plays the role of the controller, right? So if this daemon sees a gas molecule coming from the left to the right, and this molecule is fast, he opens the door and he lets this fast molecule, through this door, coming to the right. And if he sees a slow molecule coming from the right to the left, he also opens the door and he lets the slow molecule coming from the right to the left. Now after a while, we can see many fast molecules will be concentrated in the right side, and many slow molecules will be concentrated on the left side. So the entropy of the system is decreased, right? So basically, we can consider this Maxwell's daemon as a controller. He can decrease the entropy of the whole system, right? But this entropy reduction is not free, because we have the second law of thermodynamics. If we consider an isolated system, the entropy cannot be decreased simultaneously, right? So it must have some extra input, right? For example, the Maxwell daemons can get some external information, which is called the lag entropy, which was proposed by French physicist Léon Brillouin in 1959. So informally speaking, if we want to counteract the entropy reduction, this controller or this Maxwell's daemon leads a negative entropy of H0 minus H. We know H0 is the bigger entropy, right? H is the entropy after the control. So since we decrease the entropy of the system by H0 by minus H, then the controller or the Maxwell's daemon needs to get a negative entropy from the outside for at least this amount, right? Otherwise, the second law of thermodynamics will be broken, right? So equivalently, the computation is at least H0 minus H. But this is informal. This is just a very intuitive explanation. It's informal, it's not rigorous, right? So next, we can use the information theory to study this problem. We can get very rigorous result. So we studied this problem in this paper. I collaborated with my friend Husheng Li, who is an expert on information theory, and our previous department head, Kevin Tomswick, he's an expert on power systems, and my colleague Sadiq Juadi, who works on control systems, and my friend Jubin Song in Korea. We studied the entropy control for the cyber-physical systems in this paper. So basically, we model the physical dynamics as a finite state system. In the future, we will extend it to continuous systems, continuous state system. But now we are just considering finite state system. So this finite state system will be perturbed by random noise. And we make observations on this finite state system. And the sensors will send out messages to the controller, and the controller takes actions. And this action will make some control on this system. So basically, it's a discrete system. And we have some technical assumptions. And in each cycle, the system state is after the random perturbation, we get a system state x0, right? The sensor sends out a message M to the controller. The controller takes action A to change the system state to X. And we want to decrease the entropy of X from the entropy of X0, right? Then we proved a very interesting lemma. So basically, we proved that the entropy reduction must satisfy this equation. So we can take a closer look at this equation. We know this Hx0 is entropy before the control, right? It's larger, right? After the control, we can reduce the entropy, so we get Hx. So basically, the left-hand side of this equation is the reduction of the entropy, right? And the right-hand side, we know I is mutual information. Ix0 and M is the mutual information between the system state before the control and the message. So basically, this is how much information about the system state brought by the message, right? And this is a malus. We have malus here, and then we have a mutual information between the system state after control and the message. So basically, we can see we have this illustration. The sensor sends out this amount of information in the message, right? Because it's mutual information between the system state observation and the message, right? So the sensor sends out this amount of information. Part of this information is used to reduce the entropy, and part of this information is left to the entropy. So we call this part the residual entropy. And it's highly possible, as we will show, that it's highly possible that this residual entropy is not equal to 0. That means you cannot use all the information sent out by the message to reduce the entropy. You have to leave some residual entropy to your system state. So this is something like the Carnot heat machine, heat engine in thermodynamics. We know for the Carnot heat engine, you cannot use all the energy to the work, right? This is similar. You cannot use all the information to reduce the reduction. You have to have some left over to your entropy, right? So this is a very interesting result. And we have also shown some upper and lower bounds for the residual entropy. We proved that the residual entropy left to your system state is smaller than or equal to this complicated mathematical expression. And the lower bound, we also have a lower bound for the residual information or the residual entropy. You have to leave at least this amount of uncertainty to your system state. You cannot completely use your information from the message to reduce the entropy. You have to leave some left over to the system. And we also studied the controller design. So basically, the controller design is the mapping from the received message to the control action. So basically, it's a function G mapping from the received message M to the control action, right? And since we want to maximize the entropy reduction, right? Then the optimal controller is to minimize the residual entropy. So we want to find the optimal controller such that we can minimize this residual entropy, because I have proved that this is the leftover of the entropy to the system state. So we want to minimize it. And we proposed a concentration controller, which is pretty simple. We want to find the destination state, a desired system state. And for the received message, we can do the maximum likelihood estimation to estimate the current system state. And then we find the control action such that we can push the current system state or the estimated system state to the desired system state. So this is pretty standard in control, right? We do system estimation and then we do the control, right? But and we have shown that for two special cases, for example, there are only two system states and two possible messages, or the information carried by the message is very close to the entropy of the system state. In these two cases, we can prove that this concentration controller is optimal. But for the general case, for the general case, it's still an open problem. We're still working on this problem, and hopefully it's something related to the problem of information bottleneck. I'm still looking into this problem. And another study is the message design. That is, given your current system state, given your observation on the system state, how to map the system state to the message, right? So that's it could be a channel coding or a source coding, right? Or it could be a joint channel and source coding. In our paper, we just studied the source coding, and we assume that the communication channel is free of errors. And we have proof that in certain cases, say a system only has 2 messages, and we have this technical assumptions. In this case, we have shown that the concentration controller is optimal. And the optimal message design is to assign the 2 most probable states to 2 messages, regardless of the allocations of the remaining states. But for the general case, we're still trying to find a systematic approach to optimize both the controller design and the message mechanism design. And we did some simulations. We considered a generator model. We use swing equations to describe the system dynamics in the system state. For the jumping probabilities among different system states, we got the parameters from the real measurement of the frequencies in the power grid in different locations of the United States. And I would like to thank my colleague, since I copied the data from her. They have a network to measure the frequency values in all United States power grid. And we did some simulations. This is one of the simulations. So if we don't do any control, we get this amount of entropy in the system. And if we propose some control, and then we get this amount of entropy, which is lower than this entropy, right? And it's a function of the number of messages that we have in the system. So if we have something like 6 messages, we can decrease the entropy to almost zero. But this is based on some very ideal assumptions. We assume very ideal controls on the power grid. Currently, we are thinking about more practical controls. For example, we are considering the power system stabilizers or the wide area frequency control to make it more practical. And our future studies, basically, we want to get maybe some NSF project from this study. For example, from the program of CCF, since this is quite theoretical. And in our future study, we want to extend the finite automation case to infinitely demanding state, or maybe continuous system state. And we want to study how to optimize the controller and the message design. For example, how to optimize the source coding and channel coding according to the characteristics of the systems, physical systems, physical dynamics. Actually, we have one conference paper to study this problem, and we got the best paper award of ICC in 2011. And also, what about the distributed sensors? Can we apply the slapping wolf coding to this system design? Or how about we have multiple Maxwell daemons? That is, we have multiple controllers. How to coordinate the actions of these controllers, right? And another idea is, how about considering the whole system, including the sensor, the communication, the controller, and the physical dynamics as a whole system? And we can say this is a computing system because we have input, we have output, right? We can even model it as a Turing machine, right? Then we can apply some interesting theories in thermodynamics. For example, the Landauer's principle to compute the minimum power consumption for sustaining such a computing system. And we have written this idea into this paper, but it has not been published yet. So this is the first question. We studied the communication requirement from the viewpoint of thermodynamics. Then the second question, second problem, given some communication requirement, given some communication resource, for example, power or bandwidth, how can we design the communication network? So basically here we want to discuss how to use the theory of a hybrid system to design the communication network. So basically we propose two approaches for the communication network design for network control or separate physical systems. The first approach is we want to jointly model the control and communication in the same framework, and then we do a joint optimization, right? So in this way, we can get the optimal performance. Maybe it's not practical, but we know what's the optimal performance, right? We get a benchmark, right? So we will discuss these details later. And the second approach, we can design an interface between the communication and the control, such that we can reuse the existing control strategies or communication standards, right? One of the possible approaches, we call it virtual queues. So that means for each packet, we can measure the useful information amount in this packet for the purpose of control. Then we can maximize the throughput of the useful information, not the original number of bits. So we published this idea in a workshop on separate physical systems. And another possible approach is to design a QoS, right? So the controller can tell the communication system, okay, I hope that the delay should be within this amount, and your packet drop rate should be within this amount, right? So this is a very natural interface between the communication and the control. And we published one paper on the QoS routing for smart grid. And it's in Global.com. It has been well cited. So since we don't have time to discuss both approaches, we focus on the first approach. That's a joint design for communication and control. And we want to use hybrid systems to study this problem. So since we want to use hybrid system, first I need to explain what a hybrid system is, just in case that you have not learned this concept before. So basically, the feature of hybrid system is we have both continuous and discrete system states. And this is an example. It's a linear switching system. We have continuous valued system state X, and U is a control action, W and N are random factors, right? And Y is the observation. So if we don't consider the discrete system state K, this is a very standard model for linear systems, right? But here we have the discrete system state, K. K can take values something like 1, 2, or 3. When we change the value of K, we are changing the patterns of the dynamics of the whole system. So basically, it's something like when we change K, when we change the discrete system state, we are switching among multiple modes for the continuous valued system state. And we want to use this to model the separate physical system. So the basic idea here is we can define a communication mode in the communication network. For example, in the physical layer, we can define modulation or coding, right? When you use QPSK, that's one communication mode. When you use BPSK, that's another communication mode, right? Or in the MAC layer, when you have different active communication links, you have different communication modes, right? Different communication modes, that means you choose different MAC layer actions, or you choose different modulations or coding. It will result in different dynamics, different modes of the physical dynamics, right? Because you have different packet drops and different delays. So in the hybrid system modeling, we can use the continuous system state to model the physical dynamics. And we use the discrete system state to describe the mode of the communication network. So basically, if we go back to the linear switching system, we use this K to model the communication network, since communication is digital, right? And we use this continuous system state X to model the continuous physical dynamics, for example, the power grids, right? This is one of the examples, and we published one paper in IEEE Systems Journal on this idea. Basically, it's about the scheduling in the MAC layer. Let's consider this a simple system. We have two sensors, S1 and S2. We have one controller. Since we have limited communication resource, for example, we have only one communication channel, only one sensor can transmit at a time, right? So we can either let S1 to transmit or let S2 to transmit. And actually, this is a sensor selection in controls theory, right? So we have for this problem, we have two communication modes. In the first mode, we let sensor 1 to transmit. Then we get this description of the system state. Let's assume that it's linear. The basic thing here is we have this observation matrix. Here we assume that X, the system state is two-dimensional, right? S1 observes the first dimension of X1, xt, right? So since only the observation of the first dimension of the X can be sent to the controller, we have this observation matrix. In the second mode, we have this observation matrix, right? Since we have different observations, then we have different control actions, right? So when we switch between these two modes, we get different patterns of the communication of the physical dynamics. So that means the communication mode will determine the pattern of the physical dynamics. Then we studied two fundamental problems. One problem, we call it mode provisioning, which is offline. That means, how can we determine the set of communication modes? For example, how many modulation schemes should we prepare, right? We want to switch among different communication. We want to switch among different modulation schemes, right? Since we can use the software-defined radio. And mode scheduling, that is, given the current observation on the system state, how can we determine the mode of the communication network, right? So here we only have time to give a very brief introduction to both problems. For the mode provisioning, basically we know that is how to determine the set of the possible communication modes, such as modulation, coding, or active transmitter sets or routing in different layers of communication network. And our principle is we want to guarantee that there should exist at least one scheduling scheme for this set of modes such that we can stabilize the system. And we applied it in the context of voltage control of a 4-bus power network. And we published one paper in JSAC, that's the first special issue on smart grid, with my friend Husheng Li and my advisor, Vince Poor. And we modulate the problem as an optimization problem. We want to minimize the number of routing modes such that we should satisfy the constraints on the communication resource and the stability of the system. And we proposed some heuristic approaches to solve this routing problem, this optimization problem. And in some situations, we found that we need at least 2 routing modes to stabilize the voltage. For example, in here we have 4 sensors, we have 4 controllers, we have 8 relay loads in the communication network. And we found that for certain cases, we need these 2 multicast routing schemes. If we switch between these 2 schemes, we can stabilize the system. But if we just stick to the first routing scheme or the second routing scheme, the system cannot be stabilized. For mode scheduling, we know that is we want to find a mapping from the current communication mode, from the current observation on the physical dynamics to the action of the communication mode. For example, when you see the voltage in the power grid, how can I select the modulation scheme for my wireless communication, right? And we modeled it as an optimization problem, such that we want to find a strategy such that we can minimize the expected cost of the physical dynamics. And the constraint is, say, the system dynamics. And we can reuse many algorithms in the theory of hybrid systems. Since I'm not a control guy, so we can use many existing algorithms in the theory of hybrid systems. And we applied this framework to the MAC layer scheduling. And we assume that not all the sensors can transmit simultaneously. So so the communication mode is a selection of the simultaneously active sensors. So that's the sensor selection problem. Or equivalently, that's how to choose the observation matrix C, right? And in communication, we know this is a MAC layer scheduling. And we model the cost as a LQG problem. And we use the dynamic programming or the approximate dynamic programming to optimize the scheduling. And we can even decentralize the scheduling algorithm. So in this paper, which has been accepted by IEEE Systems journal, we applied this framework to the voltage control for multiple distributed energy generators. And the system state is the deviation of the voltage at these access points to the main power grid. So we want to drive all these voltage deviations at these access points to 0, right? We want to drive all the voltages to the desired value, right? So we can use a linear model to describe the system dynamics. And we did a lot of simulations. Here we just show one of the results. If we use round-robin scheduling algorithm for the sensors, that's the simplest, right? So all the sensors take turn to transmit, right? That's round-robin. Then we get this amount of cost for the voltage control. And if we use our optimization framework and we let the sensors to broadcast a few bits for their priorities, then we get this curve. So we can see even if each sensor just broadcasts 1 bit, we can still reduce some of the cost. And if it broadcasts 3 bits, we can reduce the cost of the voltage control by almost half. So that means our proposed approach is much better than the simple round-robin scheduling algorithm. So all the previous studies on the paper, we either derive bounds for the performance or we do simulations. But my students are also doing real implementations. My students are implementing the communication network for the DECC lab at Oak Ridge National Lab. So they have a microgrid test bed, but they don't have communication infrastructure. So my students are building the communication network for them. Basically, we have both wireless communication and we also have optical fiber communication. So it's quite a hybrid. And we also built a test bed for co-simulation for the Wi-Fi communication network and the power electronics control in microgrid. And this is implemented in MATLAB Simulink. So for both parts, for the Wi-Fi part and the power electronics control part, both are quite professional. And it took us a lot of time to synchronize the timing information in both the communication and control systems. And our future research on this topic, we want to propose more efficient algorithms. And we want to compress the possibly huge space of the communication modes. And we want to incorporate the algorithms in practical standards or protocols. So this is a second problem. And the last problem is about the security. We know in a cyber-physical system, you can attack the system, right? You can inject false information. There could be multiple modes of the false information injection. For example, when you take measurement, you can physically perturb the measurement, right? Or when the sensor sends data to the controller, you can inject you can hack into the system, and you inject false data packet into this the system, right? So that's a false data injection attack, and it has been studied by many people. But most people forget this thing. In many cases, the sensor also needs a very precise timing information. For example, in power grid, the phasor measurement units, PMUs, need a very precise timing. And they got the timing from GPS. But we know we can attack the GPS. We can do GPS spoofing attack. So my research group studied the GPS spoofing attack on the timing information. So basically, the GPS spoofing attack has been demonstrated a few years ago. They have the attack is not difficult, and the device is not expensive. They told us you just need $1,000 to build such a GPS spoofer. And the mechanism is also quite simple. The GPS receiver gets the timing information by doing correlations to the code in the GPS, right? If it finds a peak in the correlation, then it captures the GPS signal, right? But we can send a stronger false signal, right? Then the GPS receiver will find another peak which is higher. So the GPS receiver will switch from the true peak to the wrong peak. So in this way, we can attract the GPS receiver to the wrong signal, and then we can provide wrong timing information to the GPS receiver. So in this way, we can fool the GPS receiver, and we can fool the phasor measurement units in smart grid. Then we studied how much damage this will cause on the smart grid. And we published one paper in IEEE transactions on smart grid. So we studied the damage on the fault detection and location in the transmission line. And so we don't have time to explain the details. Basically, we have two indicators to indicate the possibility of a fault over a transmission line. And we found that if one of the sensors at the two ends of the transmission line is attacked by the GPS spoofing, then the indicator will be increased. So that means actually there's no fault. But once I attack your GPS receiver, the controller will think that, okay, there is a fault at this transmission line. Then it may trigger the relay protection, and it will isolate this transmission line. But actually there's nothing wrong there. So this will bring damage. And another interesting example is we can use PMUs to locate the fault in the power grid. For example, we can use 4 PMUs at Chicago, Kansas, Atlanta, and Blacksburg to detect the location of the fault. So maybe the true location of the fault is in Mississippi, but we can attack the PMU at Blacksburg. Then once we attack so according to our simulations, we do a reasonable GPS spoofing attack at Blacksburg. Then the system will think, okay, the location is actually in Kentucky. So it is completely wrong, and the system will take wrong actions. So this will cause a lot of damage, right? So we have demonstrated a lot of damages on the smart grid. And we also studied how to do the defense against the GPS spoofing attack, such that we can protect the timing information for cyber-physical systems or for control systems. We published one paper in IOM, which is the most important conference on GPS. Basically, our idea is we use 2 antennas with different radiation patterns. Then we basically, this is an illustration of our experiment. We put 2 antennas there. One antenna is so basically we have different radiation patterns for these two antennas. And then we compute the standard deviation of the carrier to noise ratio between the two antennas. Then we plot the standard deviation, the distribution of the standard deviation in different times in this figure. So this red curve shows the curve for the GPS spoofing signal. And the black curve shows the curve for the true GPS signal. So we can see it's quite different, right? So we can use these two different curves to distinguish the true GPS signal and the wrong GPS signal, right? But we still have some overlap here, so that means our detection, there will be still some mistakes in our detection, right? So then we seek help from the upper layer. We know in the upper layer, when we receive a lot of data from different sensors or different PMUs, they have redundancies because they make different observations on the same system. So we have redundancies. Then we can try to distinguish the abnormality of certain PMU reports, such that by cross-checking. This is a scheme proposed in our paper. We have multiple PMUs. When we detect the abnormality of this PMU, we use the data from all other PMUs to do a prediction for this guy. For example, we can use Kalman filtering, right? Then we compare the prediction from all other PMUs and the true reports from this guy. Hopefully, there should not be a big gap, right? If there is a big gap between the report from this guy and the prediction from all these guys, hopefully something's wrong, right? Then we can evaluate the trustworthiness of different PMUs, and we determine the control action according to the trustworthiness of different sensors or different PMUs. So in this way, we can design a control system based on the framework of trustworthiness. And then we combine both detections in the upper layer by comparing the reports of the PMUs, and the physical layer by comparing the physical layer received signals, right? Then we can do a cross-layer detection, right? And we published one paper in the ICCPS, which is a conference, very good conference on CPS, cyber-physical systems, which will be held in Philadelphia next month. I will go there to present our paper. So we have found that if we combine both upper layer and physical layer detections, we do the cross-layer detection, we get a much better performance. And this work is done by multiple agencies. So it's done by my student and my collaborator in Australia, and this guy who is he's a leader of the power group in Oak Ridge Election Lab. So we're quite satisfied with our result. So along this direction, our future work is we want to do more field experiment, collaborating with Oak Ridge Election Lab, and we want to have more experiment characterizing the spoofing signals, and maybe the case of multiple spoofing GPS spoofers. Another interesting thing is we also want to extend this problem from smart grid to the air traffic control, because for air traffic control, each plane gets its own location by from the GPS, and it broadcasts its own location information to all other planes, such that we can do the air traffic control. But what if the GPS signal is attacked? They have never considered this possibility. So we're collaborating with my friend to study what happens if the GPS is spoofed when we do air traffic control. Is the system robust, or it will cause a lot of damage? So this is we're still in the beginning stage, but it's quite an interesting study. So conclusions. Basically, we studied 3 problems for the the information network in separate physical systems. The first problem is the fundamental problem of the communication requirement. What's the minimum communication requirement for controlling physical dynamics? So we studied this problem from thermodynamics, which is quite informal, but it's quite interesting. And then we get rigorous results from information theory. And the second problem is, given communication resource, how can we most efficiently design the communication network? So our idea is we want to integrate both communication and control into the same unified framework. For example, we can use it as a hybrid system to model the whole system. And then we do the optimization in a joint way. Then in this way, we can get the optimal performance. And then we want to compare this performance with the performance obtained from separated design, right? And the last problem is the security problem. That is, how can we protect the timing information in a control system? Because we know in many cases, timing is very important for the control, right? So if someone can attack your GPS, how can we evaluate the damage, right? How can we protect our system from this GPS spoofing attack? So for all these three problems, there are still a lot of ongoing research, and we are expecting to get some research funding for these three topics. And hopefully in the next 5 years, we want to get more details. We want to solve more open problems, at least to fill our curiosity. Right. Okay, so this is my talk. This concludes my talk. Any questions? Yes?
Entropy is a pretty abstract
Yeah.
theory of merit, so I'm wondering if you can describe a classical system where lower entropy leads to a more obvious figure of merit like stability. And I kind of have in mind there's biological systems where the entropy can be too low.
Okay.
So is there like a classification of the systems that you're looking at?
So here we just work on a very general system, and we want to make the system as certain as possible. So we want a low entropy. But you mentioned in biological system, a low entropy may not be good, right? So that's very interesting because in my thought, low entropy is always good. But if we consider, if we don't want to control we don't want to reduce too much entropy, then maybe we need to add more constant to our proposed algorithm. Yeah. But that's a very, very interesting problem. Maybe we can talk offline, because I really want to know what's the damage of low entropy brings to the biological system. Okay, power line communication, that's very interesting, but the problem is I don't have a device. So I don't have measurement devices. I don't have a power line, long power line. So I don't just want to do some simulations. If I don't have real experiments, then I cannot quite convince myself about the validity of our algorithm or protocol. But that many people are still working on it, especially in the distributional power network, since the voltage is not so high, so it's quite efficient to reuse the power line to do the communications. Or maybe it can also be used for the control in a microgrid, maybe. But for a high voltage transmission line, that may be difficult, because the signal cannot pass the transformer. So when it hits the transformer, then it's stopped. Or maybe you can design an adapter such that you can change the power signal to another type of signal, and then it goes around the transformer. Yeah, that's possible, but I don't have research on it by myself.